Good evening, all. I hope you're all doing well. Students, I request please inform your friends to join the session as there are very 22 participants. So please inform your friends to join the session as soon as possible. Okay, we will start for the day. Good evening, Shashank sir.
Yeah, I think I can hear my voice.
Yes, sir. You're audible.
Yes. So we'll start. Right. So we'll continue from what we had to continue from yesterday's. Yesterday, actually, we were discussing about the LSTMs, bidirectional LSTMs we have seen. And after that, we have started with the attention mechanism, right? And we have to continue that attention mechanism. So I'll just share my collab screen. So directly we'll go to the practical part. I'll just share my collab. Okay. Okay. So let us understand from where we have actually left off yesterday. But first, you know, trying to understand that, about this attention mechanism, which is the sequence to sequence model. Okay. So this sequence to sequence model, as we have already discussed, this is actually based upon the concept of encoder and decoder. Okay. So it is based upon the concept of encoder and decoder. So that also we have seen. And in the first step yesterday, what we have done basically is to, So here I've added some comments also when we were actually discussing, correct? So this torch, right? It's a library which we are using for core Python. Okay. And then we are implementing this torch.nn also, which has the neural networks inside it. Okay. So this function we have actually, or the library we have incorporated into our, Python notebook. And we have started by first, inheriting the class, right? So this nn.module will inherit all the PyTorch models into the, Python notebook. So here class encoder indicates that encoder is nothing but a new class or a new function which we are trying to define. And then from there, we understood step by step where we have defined a constructor, right? So we have defined a constructor, and after that we have defined the size of the input vocabulary, the size of the word embeddings, right? And after that we have also given the hidden states, right? And also we have given the number of layers to build the GRU model, gated recurrent unit model. Okay, so that also we have seen. After that, we have given the dropout function as well. So this basically dropout function is basically helps us to prevent the overfitting for the model. Okay, and after that we have given the function super dot double underscore init. This function basically initializes the class. So this also we have seen. After that we have given the embedding function. All right. So this embedding function will define each word, right? Embeds it, right? And it creates the tokens, right? So already you guys know what is token because we have already seen the tokenization. After that, we have built the model, or we can say we have given the input, which is the GRU, okay, gated recurrent unit. For that, we are using the neural networks inside the PyTorch. Okay. After that, we have given the dropout function, right? And from there, we have defined the forward function. Okay, so this is what is the first step what we have done. After that, we have seen or we have started with the decoder part. Okay, so how to how to implement the decode or apply the decoder part for the sequence to sequence model. After that, here we have defined the softmax function, right? So this softmax function, in that we are trying to use the forward pass. Okay, so we are applying softmax and the forward pass. Okay, so we already know, no, there are bidirectional forward pass as well as backward pass. And after that, we have actually defined the class attention, because we are trying to understand this attention mechanism, right? So we have defined the class attention. For that, we are inheriting the features whatever are there, right? For this attention module, right? We are inheriting it from the I would say the PyTorch library. Okay, so NN is the neural networks inside the PyTorch. Okay, now after that, we have given one by one, which is encoder, decoder, and the attention dimension. So the first one is the hidden dimension inside the encoder. The second one is the hidden dimension in the decoder. And attention basically gives the size of the intermediate attention. Okay. Then after that, we have also defined or described the self-attention as well. Okay, because these are all self-paced, self-learning mechanisms. And then we have given the self, which is the attention score. Okay, so that also we have defined. And after that, we have taken the forward. Okay, we have taken the forward pass function. Okay, so till here I just have done, correct now? And after that also, I have just defined this batch size, right? And the output of the encoder. This also we have seen. After that, we have seen this tan h function also, I remember telling you, right? So it's basically an activation function. So tan h is nothing but a tan hyperbolic function, which is an activation function. So after that, giving the self-attention, right, and returning the or applying, I would say, the activation function. Here you can see applies the softmax to normalize the weights. Okay, so this is what we have actually applied. Then after that, we are applying the decoder part. And for this decoding, the same thing what we have written here, you can see. Okay, so whatever we have defined for attention, the same thing here also will be there. That is why here I'm not adding any comments. Okay, the functions are same. Only the coding part actually varies here from what we have written before. Okay, the same init function, the same self, output dimension, embedded function, hidden dimension for the encoder, hidden dimension for the decoder, dropout, right? Attention, everything is the same. Okay, the same GRU model also, right? Gated recurrent unit for the things also. After that, applying the same here also. Here I've added anyway a few comments. Okay, so this input basically is for the batch size, and this hidden is for giving the number of layers. Okay, this output encoder underscore output gives you the length of the batch. And we have already discussed what is batch size, right? And after that we have we have a thing called as an input. Okay, and then comes the self drop, or I can say dropout. Okay, and then we add the attention weights. So here actually this one is fine forward. Let me check for a few things. Anyway, I've added some comments, but let me check anything more I can add so that it will be easy for you to understand. Here, just give me a minute. So anyway, this one is fine. For forward pass also, I don't think you require self-hidden encoder outputs. Okay. Let me see. Here anyway I've added. So class decoder also. I don't think you require. Okay. So probably for here um, you may require. This probably we can add here. So for self-embedding, so dimension and embedded dimension, we can add this comment. So creates embedding layer for the target language. So they can add this. And for the next line, self RNN, for that applying the GRU model. So basically it converts. Okay. It inputs the DRG model and outputs the decoder model, or you can say decoder hidden state. Okay, so that is the uh, comment for that. Okay, now it will be fine. So self FC underscore out. We are FC is nothing but the final layer what we are applying. Okay, so let me add that comment also, because I kept a few comments to add. Okay, for a better understanding. Okay, so this FC is nothing but the final layer which combines the attention layer with the RNN outputs for embedding. So then after that, self dot dropout. This is a normal anyway. You guys anyway know that, but if I'm just adding it, so just a regularization layer. It's just a regularization layer. Okay. So this should be fine. Okay. So if you want some gaps, you can put the gaps. I don't think we require. Just for you guys, I've added the comments also. Okay. Okay. Now, after that, we have this forward. Okay. So for this forward, I can add one comment. I felt this would be more appropriate. So let me add a comment for this. Okay. So this one basically performs a one-step, decoding step for a single token input. Okay. And this is what the other comments basically are. Yeah, just let me save some space. Okay. So after that, that part, we have this unsqueeze. Okay. This unsqueeze is nothing but, converting the batch size. Okay. So let me add that also. Here I will add. Okay. Yeah. Convert the batch size to 1 comma batch size here to stimulate. Now let me remove this comment. More than this, this comment will help you to understand in a better way. Okay. And after that, we have this embedding layer, right? So for this embedding layer, what we can put is, let me add one more line here. Okay. So I will remove this. Okay. A few things anyway I've added before, I'm just modifying, for your comfort. Okay. And here for the attention weights also, we have the self attention. This will basically compute the batch size. Okay. You can put like this. Okay. And after that, we have this attention for unsqueeze one. Okay. For that, we can add this reshape. Okay. Because this is basically applying the reshape function only. Okay. Yeah. So this is basically for reshaping. I think now the comments look better. Yeah, that's what I just thought of adding a little more depth comment so that it will be easy for you to somehow, try to understand. Okay. And here, this is what one is for the embedding layer. Yeah. First, usually we have the unsqueezed part. Then we have this self-embedding layer. Then we have the self-attention layer. Then we'll have the attention layer. So this is the steps in it. Now, what will happen is this basically uses the encoder. Okay. For encoding the output, here I mentioned anyway, but what I'll do is I'll just remove these comments and put a line here. Okay. Add it to the next line. This has become typical. So here we have added one encoder input. You can see here. This encoder input actually changes the shape from SRC length. SRC is nothing but the sequence. Okay. So sequence length, batch size, and the hidden layer. Okay. Of the encoder, right? To the batch size, sequence length, and the encoder for the hidden dimension. So that is the pattern which it is going to take. Okay, so that is the next one. Now let us go to the next part, which is the weighted encoder. Okay, for the weighted encoder, what can actually happen is I will just rechange the comment. Okay, so I just have one context and okay, let me add it to the next line. These are big comments, so the problem is it will go side, so that is difficult to see. So, yeah, okay. Now, if you see carefully here, weighted encoder outputs, here we are applying the torch function, okay? And for this torch function, right, we are applying the attention, right? Now you can see attention weights. Now what is exactly going to happen is, it is going to batch the dot product in the attention weight. Now in easier and a simple language, if you see, this basically takes a dot product. There's a function called as a dot product in math. Okay. So this is basically, this dot product is calculated between vectors. Okay. So what it does basically is it takes the dot product between the batch size, right? And the one is nothing but the dropout. Okay. Here you can see. I don't know whether it's showing in this case. Something it is showing and doing. Okay, leave, no problem. This is basically, dropout. And this is basically what it does is it regularizes using the encoder hidden dimension. Okay, so it will permute in this order. Okay, so that is how this weighted encoder. So in a simple language, even more simple language, if you want me to explain, we can say that it is adjusting the weights. Okay, in a simple language, because but the problem here is, if you understand that, okay, it is just calculating the weights, there is no use. Okay, logically, if speaking, because that is how what normal people try and understand. But being a a person who's learning generative AI, that is not sufficient. So you have to understand at which level the dot product is actually applying in such a way that where the dot product is being applied in such a way that how it is actually giving that weights. Okay, sorry, it's calculating those weights and giving the attention based upon the weights. So that is the most important scenario for you to understand at this level. Okay, now let me go to the next line. Here you can see there is input for this. Okay, so for this, what I will take is, okay, there is this. So I'll add here for you. Okay, Now you'll be able to understand what has happened here. Okay, from exactly uh, you know what is supposed to happen from the previous step. Now here you can see that this actually concatenates. This cat function is nothing but concatenate. Concatenate, I think you might be knowing, that is basically putting two things together. Okay, so we are using the concatenate function. Okay, between the batch size and the embedding dimension. Okay, that's it only we are doing here. Just we are creating, dim is nothing but the dimension. So we are taking for two dimensions. Okay, so now let us go to the output, which is the hidden layer. Okay, so what does this hidden layer actually try and do? Okay, now for this, let me add one comment. Okay, so anyway, my down comment, I want it to be there. So it basically converts from output batch size to the hidden layer. So if you are feeling bit of tough on these two, probably you can remove. I just want to be, I just want these to be here in a very simple language, because I'm trying to simplify as much as possible, and add comments. That is even more the tough part, because I have to tell the technical things. I cannot just simply tell on the just the outer picture and leave, right? So here when it comes to the output layer, so just this output and input hidden layers, you just keep it like this. But to understand on a simpler note, you can see that it is passing through the GRU, because that is what what we are actually trying to use, which is the gated recurrent unit. So here we are outputting the shape, okay, to the batch size as well as the hidden dimension. Okay, so that is what actually it is happening. So now coming to the embedding part or embedded part. Okay, the most important thing what this embedding is basically doing is this is uh you know removing the dimensions. Okay, this is basically removing the dimensions, and it is setting it back to the batch size. Okay, setting it back to the batch size. That is what is actually happening. Now coming to the next part, which is the prediction part. Okay, so for the prediction part, for the here, what is basically it is taking is, let me just one more comment here. Okay, so what this this particular, we are for this prediction, we are using this concat function. Okay, so anyway, for example, if you are not understanding any one particular step, you can use the Google Gemini also. Okay, it will try and help you out as well. Okay, so here, to understand on a bigger picture, this is basically concatenating, right, the final layer. Okay, it helps to build the final layer in a simple language. This is basically helping, the torch is helping to build the final layer. So that is what is actually happening. Okay, so this is the main thing here. Now coming to the prediction part, what this is happening. So let me add one comment here. Okay, and we'll go to the next part. Okay, yeah, so this will help you. Okay, so this prediction basically is unnormalizing the scores logits over the vocabulary. Again, if you are not aware of what is logits, logit is nothing but a logistic regression. Okay, so probably you can just understand, try to understand the what is logits. Okay, this function logits is basically used on the logistic regression. Okay, and for the hidden scores or the hidden layers, we are trying to decode for the next step, because this attention mechanism is not over. We have one more, couple more steps as well. Okay, so now I think this is clear at this point in time. Okay, so if you are fine, good. If you are not fine, then probably you can revisit the video later. Now, what we are trying to do now is we have separately done the encoding part and the decoding part. Okay. Now we are both combining both the encoding and the decoding part. Okay. So that is what we are trying to do now. So till now, any particular any doubt if you have, you can just ask me. Just pause here, and the subtask also you can read it just for a minute. If you have any doubt, you can just ask me. So if you have any question, you can ask me about the attention. So actually, those who are learning for the first time, this might be, a bit little tricky to understand as well. I can understand. Okay. So it's not that easy also to figure it out also. Yeah, I can understand that. So yeah, that's not a problem. Slowly you can try and understand that how things work in generative AI. Okay, because this sequence to sequence model in attention mechanism is very important. And then we have this Bahdanau attention as well as the Leong attention. So these two also play a very important role, to the current day transformers which is used in the generative AI. So yeah, it's you know tough thing, but have to accept and try and understand and move on. So that is part of. Okay, fine. I think probably no questions. Can just move on. Okay. So next thing is integrating both encoder and decoder part now. Okay. So in the attention mechanism, what we have taken, we are trying to, integrate both the encoder and decoder part to build the sequence to sequence model. Okay. So that is what we will try to do now. Now let us go to the next part. Okay. So again, we have coding part. Okay. So let me go there. And let me, I think the first part of the comment you anyway know, like defining the, or I'll write, okay, probably that should be better. Let's write it. Anyway, one comment, it's okay. So, right. So here we are what we are trying to do is we are actually defining or we are calling or inheriting, I would say, right? Or we are actually creating a sequence to sequence function. Sorry, sequence to sequence function. So for that we are inheriting the neural network model from the PyTorch. Okay, and here we are trying to first we are trying to use the encoder model. Okay. So what we will do is, okay, so let us put the comment here. The first thing what we are doing is putting the encoder model. So here we have defined the encoder model. So that encoder model is basically, uh, you know, an instance of the encoder class. Okay. So that is based upon the GRU. Okay. Or you're already aware of what is GRU. And the next instance, what we are generating is the decoder class. So the decoder class is based upon attention mechanism. Okay. So that is the next one. Okay. Now, the next thing is we are giving the device. Okay. So device is nothing but the encoding through the CPU or a GPU. So here CPU is through an you might be aware of what is CPU. So here you are giving CUDA. CUDA is nothing but a GPU. Okay, I'll write it here. It will be easy for me. Okay, so it is evaluating or executing using the GPU. Okay, so after that we have the super init function. So the super init function is basically used to initialize the base class. So already we have done this in the previous step. So it is easy for you to understand that. So now going to the next part, right? There is one particular function which is called as the teacher forcing ratio. Okay, so this teacher forcing ratio is nothing but how much of probability will be there, okay, for applying the teacher forcing. Okay, so this ratio usually, uh, we can take 0.5, but if we increase the teacher forcing ratio, I would say it is the input should be very, very practical, very good, right? And the input what we are taking to train the data and build a model should be more good. So here, if you see in a simple language, uh, if you write 0.75 as the teacher forcing ratio, right? That means we use 75% of ground truth inputs. Okay, so it is very difficult to balance them, whether it is whether it is 75% or 50%. So based upon the scenarios, you can actually do that. Okay, so that is one way to understand it. Now, even in a single, it is maybe I will do one thing. One small line I have. Uh, Maybe I'll just put that. Okay, it will help you to understand. Okay, so this might help you to understand. Let us not take this 0.75. Okay, this will be a bit confusing. Okay, yeah, so you can understand like this now. So this teacher forcing ratio, that is basically a probability to use the ground truth tokens. Okay, so token is nothing but the tokenizations tokens only, those only. As the next decoder input helps faster convergence. Okay, fine. So this is what actually this does. Okay, now coming to the next step, here we are initializing the variables. Okay, the first part is to initialize the variables. Now here we are giving the batch size. Okay, for this let me add a comment. Okay, this should help you. So number of sequences in the batch. And after that, we have something called as a target length. Okay. So target length is basically the length of each target in the sequence. Okay. And then we have something called as a vocabulary size as well. Okay. So this basically gives the size of the vocabulary. Okay, all these things anyway we know by this time. Already we have seen this. So next thing is preparing the tensors. Okay, so anyway for tensor I have just mentioned tensor to store. Yeah, this should be sufficient. Tensor to store decoder outputs. Okay. Now after that encoder, we are giving the encoder output. So this basically passes through the sequence of the encoder. Okay, so self encoder is what we have given. Right, we'll do one thing. I'll just remove this. Right. Okay. I'll put this comments. This will be easy for you to understand. Okay. This should help. Okay. So in this case, the self encoder is basically an encoder. Okay. So this encoder where basically it will try to understand about the encoder outputs and the which are hidden. Okay. So that is one thing. Now the next part is the target. Okay. Or you can say the first input you can think of. Okay. First token. Okay. Now what we will do is just add like this. And this will ask for the batch size as well. Okay, so yeah, this is what it is going to take because we are combining both encoder and decoder, right? Yeah. So next thing is we are going to take the range. Okay, so taking the range here and we are looping it. So anyway, here this function will be sufficient. After that, we are going with the output hidden layers here in this step. Okay, so in this step we are taking the output hidden layers. So here we are going with the self, I would say in a simple way, all right? The first part here, this input in this one is the current token. Okay, and this hidden will be the previous hidden layer, and encoder outputs will be the all encoder states. Okay, so that is what we are taking. So here anyway it's mentioned. You can just look into that particular function. So after that we are going with the output. So we are using the tensors to here you can see tensor holding predictions. Okay. So after that we are going to decide whether if we are going to use teaching force or not. Now here if you see here we are trying to define the teaching force. So what can happen is I hear one important sentence I wanted to add. Okay. So let me keep this. Okay, let us not take that. We'll add one more. Okay. By using this, random function, randomly we will decide whether we are going to use the teaching forcing, that is the true target, or the model's own predictions. Okay, so that we are going to decide based on the teacher forcing ratio. Okay, so that is one thing we are trying to understand. So after that, we are going to use the function argmax to actually to get the highest prediction. Okay, or the topmost prediction. Okay, or you can say top one prediction. Okay, and for that we are going to take the top one part. Yeah, I'll put like this so that this will be sufficient. Okay, so this should be helping. Okay. Now let us go to the next one, which is returning the prediction. Okay. So here we are returning the outputs for the prediction part. Okay. Now what is going to happen in a very simple way, if you ask me, the encoder, what we have taken before. Okay. So that will try to encode from the context vector. And the SOS will be the first decoder. And each time we are going to predict the token, it is going to use the previous state, right? And this teaching force or the teacher force basically decides whether to use the ground truth or the model predictions. So that we have already discussed. Okay. And the outputs will be used using the tensors. Okay. So that is the next part. So now here what we have done is we have developed an encoder as well as the decoder part. Now let us try and apply on a particular function. Here to train that or to take a particular function, okay, we are taking an input dimension. Okay, let us take an example, value, right, to apply. So the next part is to apply this here. Okay. The first part here you can see, okay, I'll just add one comment for this, not much. Here I will add, okay, it should help you. It's a very bigger comment. We'll do one thing. We'll take it to the other level. Okay. Okay, fine. So now what we are adding here is we are adding the vocabulary sizes. We are applying the embedding dimensions. We are applying the GRU's hidden size. We are applying the number of layers. We are applying the dropout probability. We are applying the attention mechanism, or we are defining. Let us not say apply. We are defining, and we are defining the pattern index for a loss function. So this is what you know, you can actually give. Okay, this one you can remove this. So that's why I just added so that you know, these comments are not required. Okay, yeah, this should help you to understand. So this comment actually can be removed. Okay, so this will help you in a better way. Okay. Now here comes the next part. Okay, so what will happen is when you are actually compiling this, okay, you will act, sorry. Okay, so here we are defining the device. This is very important, particularly when we're actually compiling a GPU based compilation. Okay, now what you're trailing is if you have any GPU, please use that. So CUDA is nothing but a GPU, right? CUDA cores. Okay. Anyway, I told you, we will talk about NVIDIA also, in the later part. Okay. Still, we have another 4 days left. No? So we will talk about NVIDIA as well. Then I will tell you in deep that what is this CUDA. Okay. So CUDA cores and all, why it is important inside a GPU. Okay. We will talk about that. So we are going to give that if you have the GPU available, use the GPU, right? So GPU is not internal graphics. Okay, don't get confused with internal graphics. It is a proper graphic card. Okay, so proper graphic card has this CUDA cores. Okay, so like the NVIDIA GPUs, okay, or the AMD GPUs as well. So if you have the proper CUDA cores, use the GPU or use CPU for compilation. Okay, so that we are trying to achieve here. Now let us go to the next part, which is defining the here what we are trying to give in a simple thing. I'll tell you. Okay, so the entire thing. What? Let me put this. Well, okay, this one is one piece of code. Okay, so what exactly we are trying to do here is we are trying to define the attention module. We are trying to define the encoder. which is using the GRU, which is gated recurrent unit. After that, we are defining the decoder, which is using the attention mechanism. Then we are combining the model using the sequence to sequence model. Here you can see. So if you want me to add, I don't think it is required. And then we are using, the compilation of the model, either by, using the compilation of the model, either by using of a CPU or a GPU. Okay. Even the CPUs are capable of compiling, but GPUs are much more faster. Okay. So that is how actually things work in reality. Okay. So that is why for all the advanced deep learning and generative AI and artificial intelligence tasks, we are using the GPUs more than the CPUs. Okay, so I will tell you in detail that what are these GPUs, how it will play a very important role, why GPUs are used. This I have a separate discussion. One session we will discuss entirely on this, because when we talk about generative AI, we have to speak about the CPU. Sorry, we have to speak about the GPUs, CUDA cores, right, and all these things as well. Okay, as a part of generative AI, we'll speak that as well. We'll try to understand that as well. Okay, so now going into the next part, which is the loss function. Okay, so here for the loss function, it tries to calculate the entropy loss. Okay, so I'll give it here. Okay, so it tries to calculate the entropy loss. So here we are giving the padded sequence. So it ignores the, here we have given ignore the padded sequence. Okay. So that it doesn't affect the training part. Okay. After that, we are giving the Adam optimizer. Correct now? So put a stop. Okay. So here this Adam optimizer will help to update the weights. Okay. So coming to the next part, we are using, I would say, we are using the iterators, we are using the optimizers, we are using the criteria. This is this part. Okay. So here, when we say we are training, okay, so we'll do one thing. I'll just put one comment. Anyway, I mentioned here, but let me also mention. Add one more comment here. Yeah. So this should be easy for you to understand. Okay. Just give one gap here. And let me also put here gap. Yeah. So here, what we are trying to define is we are giving a single epochs. Okay. So epoch is nothing but one, I've already told you, one cycle of training is what epoch is. After that, we are giving the iterator. Okay. This iterator is basically a data loader. Okay. And this clip is nothing but it actually applies for this exploding gradients. Okay. So I've shown, vanishing gradient, exploding gradients. Yeah. For that, we are going to use this. Okay. So that is one thing. And then after that, somewhere I've given the model train. I'll just show that. Yeah. So for this model train, it is very important that you understand. So this basically trains and put up the layer that the dropout in the training model. And for the epoch loss, it basically initializes the total loss. Okay. Right. So this basically initializes the total loss. Okay. So after that, we are using the iterator. I've already told you why we are using an iterator. And here we are iterating over. Okay. So basically we use the for loop to iterate over a sequence. Okay. And this basically loops over each batch in the training data set. Okay. So after that, we have one more, which is a sequence for both. Okay. So I'll do one thing, which and the comment here, because this comment is for the both. So this basically gives you an input, right? And it also gives the target, which is TRG here, you can see, right? SRC is for the input and TRG is for the output. And or the target, you would say, and these are the tensors which are connected to the correct device. So tensors are nothing but the cores inside a GPU. Tensor cores we have inside the GPU. And again, explaining about these GPUs, I will do that later. Okay. So next is after that, we are applying the optimizer for the gradients. Okay. Here we are applying the optimizer for the gradients. Okay. So 0_grad. Yeah. This is the function. So for the output, we are running the model. Okay. And we are also outputting it. Should help you. We are outputting the dimensions as well. After that, we are giving the targets. Okay. For we are actually defining the targets. These targets will actually help you this part. Okay. So what actually these do is it will exclude the first token. That is the first thing. And it will reshape both the tensors. Okay. So we will add that comment also. I would like to add because everything it will help you when you try to revise it later. It will be easy for you. Correct now? Yeah. So what this will do is do one thing, which we add it here. And so let me finish this. We'll go for a break. No. So for both the target as well as the input, okay, for both the one, it will take. So this one, it is basically formatted using an entropy loss. Okay. Okay. Fine. It's not taking. Fine. Next, we'll go to the loss function. So for the loss entropy, we are going to calculate the ground truths for the loss function. Okay. And next, we are going to apply the back propagation. Backward is nothing but the back propagation. Okay. So we are applying the gradients to the back propagation. Okay. So after that, let us go to the applying the utils function. Okay. So this utils, let me add the comment here. In CP. So basically this utils function helps the gradient, okay, basically from exploding. Okay. So that is what this utils function is. It's a very important function actually in the context of the entire modeling using the attention. So next is optimizer. here basically this updates the models for the gradients. Okay. So next is the epoch loss. Okay. For this epoch loss, what we are trying to do is let us, accumulate the loss for each function. Okay. And after that, we are going to return the epoch loss. So what exactly is this returning? It is basically returning the average. Okay. So we are calculating by using the epoch loss divided by the length of the iterator. Okay. Yeah, that is one thing. Now the next part is through the evaluation score. Okay. So the evaluation score, let us implement the model's evaluation. Okay. We are going to apply the model evaluation. Okay. So yeah, so that is still there. We'll just go for a quick break and come back. I also need a break. So we'll go with the model evaluation once we come back from the break. Okay. Okay. Just give me a minute. Okay, so we'll go for a quick break. Let me mention in chat. So if you have any doubts, you can just ping it in the, okay, you can just ping it in the chat. Okay, yeah. Okay, so let us continue. I think nobody has any doubt. I think nobody has posted anything. Okay, fine, fine. So we'll continue with the attention mechanism. Okay, so let us see the evaluation part. Okay, that is very important because we have built a model, and on that model, let us evaluate how the model actually performs. Okay, so let me share my screen. Where we are, yeah, we are at the evaluation part. Okay, fine. So now for the evaluation, let us actually use a technique. Okay. Uh, okay. Uh, so let us use a technique which probably you would not have actually seen. Okay. So to actually evaluate the loss, what we are actually trying to do is, just let me add a comment. Just give me a minute. Sorry. Okay. Now, what we are trying to evaluate here is, okay, we are also using that evaluate function as well. What exactly we are trying to evaluate is we are trying to calculate or evaluate the validation loss. Okay. So validation loss is not a new concept for you, right? We have already seen that. So basically, what is a validation loss? Validation loss is nothing but the difference between the actual and the predicted value. So always this particular loss has to be minimized, correct? So that is why now the next important thing is let us talk about the BLEU. Okay. So for using this BLEU model, okay, this particularly is a very important metric which is used in translation tasks. For example, you guys use Google Translate, correct? So this Google Translate, we can say this BLEU model is one of the applications, okay? Or you would say that Google Translate uses this BLEU model, okay? So either way, you can try and understand, okay? And that is the main thing. Now talking about the okay, so PyTorch anyway, you know this one. Anyway, I'm not adding that again. Okay, so random, but useful in this randomness content. Okay, so usually we can use like this. Okay, this randomness is basically useful for randomness control. Okay, it is very important actually to describe the random function. So that is why I have described here. Okay, got it now? Now going to the next function, which is using the corpus BLEU. Okay. Now this basically calculates a BLEU score. Okay. Or this corpus score. Okay, we put it in the next slide. Okay. So this basically calculates the BLEU corpus score. Okay. Now here let us try and understand now by step that how this evaluation function we are going to define. Okay. So the first one is the model dot evaluate. Okay. This function basically sets up, right, to self-evaluate the model. Okay. It is very important because generative AI tasks are all self-evaluating. Correct? No, we are not manually evaluating anything. It's a self-evaluate. How it is happening? One of the models is the BLE. Okay, so that is the link between using this BLE models for the self-evaluation control. So this will automatically, that is why we have defined no self dropout, self attention, right? Why we have defined all those things? Yes, because the model will be able to evaluate and it will be able to, self drop out, right, from the aspects. That is one thing. Now going to the next part, which is disabling the gradient descent. Okay. So now with, let me, I think here we have defined. Okay. So here for basically torch, we are actually giving the gradients which can improve the memory and performance. Okay. Now let us go to the iterating part. So we have given the iteration part. Here you can see for I in enumerate, right? We have given the iteration part. Even for this, I'm adding the, so this is basically using a for loop. Okay. So for applying the iteration part. So looping over all the batches in the validation data set. Okay. So that is one thing. So after that, we are basically moving the data, okay, from the sequence to the target and target to the sequence. So we have already seen that now we are using this CPUs and GPUs. Then after that, we are going with the forward pass. Okay. So here forward pass indicates, okay, I'll just add the comment here also. Okay. This, huh. So this basically, it turns off the teaching force. Okay. And this actually predicts the full sentence without actual target inputs. That means the model uses its own outputs as its next inputs. Okay. So that is the advantage of building a self improving or self evaluating models. Okay. So that is why whenever we, define an encoder and decoder for a particular model or for a particular data, when we are building a model, right, for a text or whatever images or whatever we are generating, the generative AI. So that is the main advantage of, giving these particular models. Okay. Now coming to the loss function here, here we have given a loss function, which gives the output dimensions as well. Okay. For this, if you see here, let me define this basically SOS at the position. Now there is one more thing which is actually using the cross entropy. Okay. So this basically went out of proportion. Wait, just let me uh, take this entropy loss and let me put it in the next line. That is one thing. And also the next thing is for the target. Okay. Yeah. So the next thing is also, next thing is for the target. Okay. So if this, looks bit of confusing, what we can do is we can just leave one line gap. Okay. It doesn't matter. Okay. Yeah. Just now, even I was thinking that probably we can leave one line gap. Okay. No issues. Okay. So after that, all this process, okay, the next thing is it tries to use the BLEU validator, or it tries to use the BLEU for evaluation purposes. Okay. Now, what will this actually do is this particular function, what we have set the model to evaluate, this will set the model to evaluate. After that, it will start giving the predictions. Okay, so that also we will add here. Okay, then it will try to collect the target sentences and it will try to predict them. Okay, so that is one thing. Now here we are anyway, the next step already that disabling the gradient, then looping through the batches as well. Okay. This is what we have given no gradient. Okay. So this will skip through the gradient. Okay. And the next part is basically for looping. Here you can see. So this is looping through the batches. Okay. Still want a comment? That is anyway just looping. You can just add that. Okay. This also I will add, no problem. Yeah, just want to add everywhere because you don't get that doubt at each step. So this basically disables the gradient and this one looping or loops through the batches. And the next thing is for the SR, move, this basically moves through the data. So what we will do is I'll just put it here. Okay. So it basically moves through the batch data and the device. Okay. So this is done for both these codes. So one is to from the sequence to the target and then target to the sequence. Okay. So both are done simultaneously in this case. Then next thing what we are doing is we are turning off the teacher forcing. Okay. So for that, we are turning it off and we are predicting without it. Okay. So I'll just add one more comment here. So what we are doing, we are predicting without the teacher forcing mechanism. Okay. So that is what we are actually trying to do in this case. Okay. So after that, we are going with the predictions. Okay. So we are trying to apply the prediction part here. Okay. So this basically takes the dimensions too, and this basically selects the token index at each step. Okay. Then it is the predictive sentences. Okay. So this is basically used for the prediction of the sentences. Now, next is for this bulk of code. Okay. So to tell you in a very simple way, okay. So basically, what basically this one will do, okay. I'll do one thing. I'll just add it here. Okay. For the entire sequence, I'll add it here. So the first thing what it does is it converts the tokens into indices. That is first thing it is going to do. Let me just paste it, then we will talk. Okay. Okay. Yeah. So now you can see. For this part, especially, okay. So what is going to happen? Okay. In a very simple way to understand that what is going to happen. The first thing is it converts the tokens. So to convert the token, we are going to use the for loop. Okay. So this basically for loop, we are using it for the iterations or through iterate. Okay. So after this, okay, now it actually tries to take the tokens. Okay. It tries to take the tokens first of the actual words. Okay. That is the first thing what will happen. After that, it is going to skip the SOS word. Okay. And it will stop at the EVOS. Okay. Which is the vocabulary, what I'm defining here. So then after that, it appends the predicted sentence to the predicted targets. Okay. So that is the next part, what will actually happen. Okay. Now, after that, this particular process is done. Okay. So this particular process is done. The next thing what will actually happen is getting the actual sentences. Okay. So now when we have an actual sentences, it will apply this model. Okay. So to what we are actually trying to apply. So let me add the comment here. So this basically applies to the actual sentences now. Okay. So whatever sentences are actually given, that will be applied by using the BLEU evaluator. Okay. So this will be done. So this is the step where if the word is EOS, okay, break, because that is what we have given. Okay. So like that, for each compilation, this will actually happen. And at the end, this BLEU score, okay, so what we have given, this will actually try to predict, okay, using this will. So this will actually calculate between the actual versus the predicted values. Okay. And the next part is it will return the BLEU score. Okay. So that is what on the whole is going to happen. Okay. So what on the whole, the bigger picture is, it basically computes the average loss over the validation. And then this BLEU score converts the predictions and targets to text and computes them. Okay, so this is the main approach where this is going to be applied. Now let us see what we have actually understood, or what we have seen through the analysis, what we have actually done. Okay, what are the key findings in the whole process, what we have tried to do. So the first part is we have tried to use the encoder for the sequence to sequence model. And this was actually successfully implemented using the word embeddings is nothing but the word embeddings and GRU and the dropout layers. So this is the first step what we have actually done. So after that, the second step what we have done is the decoder with an attention mechanism. And this was successfully implemented with the attention mechanism, actually calculating the weights based on the decoder's hidden state and the encoder's outputs. So this is the second thing what we have done, or this is the second identification or findings what we are able to find. So the third thing is the encoder and decoder we have together integrated. Okay, and this was actually done with the complete. This was integrated nicely with the sequence to sequence model, and this was basically incorporating teacher force as an option. This was the thing which was done. Then the training setup was completed by defining the cross entropy loss and the Adam optimizer. And we have also used the train function to outlining the training loop which was implemented. Then after that, we have used the evaluation metrics, specifically average loss and the BLEU scores. These were successfully implemented through the evaluate and calculating the BLEU functions. Okay, so this was the process which was done. Okay, so now this was the basic thing what can be done inside the attention mechanism. Now, if we go to the next part, which is the Bahdanau, these things got disconnected. Okay, let me start the session. And in this Bahdanau also, we will start. If you are not using for a long time, this will get disconnected. This one also. Yeah, this attention mechanism. Yes, it has restarted and run. So I'll share this today. Let us also try to finish off this Bahdanau's attention also. Okay, so it will be easy for you to link both of them. This one also ran. This is a bit shorter only. And since you anyway understood this attention mechanism, Bahdanau's attention will be very easy. Okay, you did not break your head too much. Okay, I know it's a bit tough for you. Okay, so probably you'll be feeling the heat. Okay. So yeah. So I'll be just briefly telling you that. Okay. Now let us go by understanding what is this Bahdanau's attention. Okay. So to implement this Bahdanau's attention, the most important thing is using the TensorFlow here, right? We have applied the TensorFlow, right? And I think you guys already know what's a TensorFlow and all those things. Okay. So to add on a simpler note, okay, because even Torch itself we have seen, so TensorFlow should not be a issue for you. Yeah, I just added what is a TensorFlow in single line. So this should help you. Anyway, we have just gone through that also. We have understood what is this TensorFlow, so it should be easy for you, right? It's a library which is used for deep learning tasks. So next thing is we have given a few things. Okay, layer, input, dense, GRU, attention, and all. So layer, anyway, you know what is a layer. Okay, so this basically adds the number of layers. Okay, so what I'll do is I'll just add a comment here. So this will add the layers, and this input function is the starting point of the applying of the Keras tensors. Okay. So anyway, you guys might be knowing anyway, because we have already discussed all these things. But let me just add quickly. Okay. So dense layer basically tries to identify the number of depth inside the layer. Okay. And then comes our GRU. So GRU guy is nothing but a gated recurrent unit, which we have already seen. This is basically a model for, I would say, this is basically a model of RNN. Okay. It's an upgraded model, okay, from the RNN. So next is the embeddings. So embeddings, you have already known, okay, because we have already seen what is an embedding. Okay. So basically converting into dense vectors is what embedding is. Okay, so word to vector is what we have used. Okay. Now, the next thing is the attention. Our most and the big hero of our model, what we are implementing, which is the attention mechanism. So it is the attention layer. So this is the layer where it is used to implement the attention mechanisms. Okay, so used in NLP models like sequence to sequence. Okay, so that is what basically this attention is basically about. Okay, now coming to the next part, which is a model. Okay, so model is basically to create a functional API is what is basically a model is. Okay, same thing only about. Okay, so model is nothing but creating a functional API. Okay, so that should be it. And yeah, NumPy anyway you might be knowing. So NumPy is basically used for numerical Python. Okay, all the mathematical or numerical operations in Python will be done using NumPy. Okay, so that is the part. Now going to the next aspect, right? Now here I'm not going into each individual aspect again. Why? Because in the attention mechanism, I have actually explained line by line, and we have almost gone through line by line. So on the whole, I will tell you. Okay. Now here I'm creating one particular class, which is an encoder class. Okay. And for that encoder class, I am inheriting the features or the functions of the Keras. Okay, so TensorFlow Keras, I am inheriting those particular features. Now, if we talk about what we are actually creating, okay, and this is basically creating a user class to basically define a constructor. Okay. So what we are defining, we will see here. Okay. Now, yeah, that is enough. We were not adding anything. Sorry. Yeah. So we have defined the init constructor. So from there you can just see. Okay. Only that particular line I'm adding. Okay. I'm not adding anything except that. Okay. I'm just defining an init constructor. That's it only I'm adding. Okay. The things which are inside, the things which are inside the init constructor, we have already gone through. So you have to, figure it out again from the attention mechanism, because we have already learned the attention mechanism. Okay, I've already explained that. So from there, you have to, try and understand that what is this init function. Okay, so I'm just giving you a hint where this init is basically a constructor method where you define the components of the encoder. Okay, so that is in where you can understand. Now, after that, we are going with the super function, right? Which is an encoder here. So let me add it here itself. Okay, I think this will be sufficient. So this super function is basically, something where it initializes the parent class. Okay, so this is from the Keras model. Okay, so that is one important thing which I want you to understand. So then we have the self batch. Okay, so for this, self batch, my comment would be they are actually in instances. Okay, so this is for both the batch SZ as well as the encoding units. Okay, so let me again add for this embeddings. Okay, so these embeddings are very important because they are basically something which converts into a dense vectors. Correct, no? So these are basically something which converts into a dense vectors. Correct? So, okay, yeah. And after that, we are applying the GRU model. So this one also you are aware of, right? But the thing here is you have a few things inside here. Okay, when you are applying the GRU model. Okay, I think this one is very important for me to tell you. Let me put this in an order. Okay, so after the embeddings, what I'll do is I'll just put a comment for the GR. Okay, now for GRU models, the first thing is the encoding units, which we have defined here. Okay, so this encoding units basically specifies the number of GRU units what we require. That is the first thing. Then after that, the next important thing is for the returning sequences. Okay, how many sequences it has to return. Okay, so that is the second important instance. Then we have the return state. Okay, so how many hidden states are there? What it has to return. Okay, that is the next and the foremost important thing. Then after that, we have one more which we have defined, which is the recurrent initializer. Okay, so this one also applies the Gloret uniform. So Gloret uniform is one particular function which is used for initializing the weights. Okay, so here also I leave some gap. Okay, should be fine. Once it's all super duper compressed. Okay, I think we are here. Okay, so too many comments than than the code. Okay, so going to the next part, we are passing the forward logic. Okay, so what we are actually passing is here we are passing the logic. Okay, so what is the logic we are passing here is we are giving the X, which is the input sequence, and the other thing is the hidden layer. Okay, so I'll put a comment here. So X is nothing but the input tensor, and the hidden layer is nothing but the hidden layer. Okay, and this is going to return an output state. Okay, that is what is going to happen. Okay, I'll do one thing. This particular comment, I'll just put it here. Too many comments with, yeah. Okay, and even this hidden also, which I have defined there, I'll put it here because it comes under that. I cannot just put it there. Okay, so this should help. So this is for the calling of the function. Okay, so we are calling the function, and there is a forward pass method here, which I am actually calling. Okay, it's a forward pass method. Okay, so after that, we have a okay, fine. So after that, we have one more important thing here, which is the self-embedding method. And for self-embedding, we are creating a dimension. Okay, so the dimension basically is, yeah. So this dimension for the self-embedding will actually input the word devices into embeddings. Okay, and this changes the shape from the batch. Here you can see that this is a two-dimension batch size and the sequence length. But this this self-embedding, it is changing into batch size, all right, sequence length as well as the embedding dimension. So it is changing the shape of that particular embedding, right? Now going to the next part, which is the output state. What does this basically do is we are anyway applying the GRU. So that you already know. We are applying the GRU model, right? And this will output all the hidden states. That is very important because this is what GRU actually gives you. Correct? No? Along with that, it will give the entire states. Okay, we'll put it in one line. The comments are bigger. Okay, so this will actually also give all the final hidden states inside. Okay, this is what, and the output is returning you the hidden sequence, and also it is returning the final state. Okay, so that is what it is basically returning. Okay, so after that, what it is going to happen is we are defining the hidden state initializers. Okay, for the hidden state initializer, what I will give you is okay, what I will create is, let me just okay. So for this hidden state initializer, what this actually will create is it will start with the hidden state with 0, right? With filling the initializers. Then what it will do is it will create the shape. It will take the batch size and the number of GRU units. Okay, and it will map with the or it will match with the number of GRU units what it expects. After that, it uses from the start, and it goes till the training process. Okay, so that is what is going to happen. So this is with the now if you see, okay, I'll just put one particular line. Okay, I just wanted this because I don't know how many of you have understood. In a simpler way, if I have to put, okay, what this is basically doing is, it is, let's put the class level. Yeah. So basically, what this is doing is the entire thing what I've explained in a simpler way. This is basically converting the word indices into vectors. Okay, so that is one thing what it is doing. After that, it feeds them into the GRU. Okay, to learn temporal dependencies. Okay, this is the second step. What is happening? And the third step, what actually is happening is it returns the sequence of hidden state as well as the final hidden state. So this is in a very simple language. Okay, what is exactly happening? Okay, but this learning is not sufficient. You need each particular step at which particular location what is happening. That is very important to learn generative AI. Okay, and so that is very important. After that, the next important thing is the developing a Bahdanau's attention. Okay, so here we have directly defined the Bahdanau's attention. Okay, so directly we have defined it. Now let us understand what is this. Anyway, we have already defined in yesterday's session. We have already seen what is this Bahdanau's attention. Okay, so let me give one line. Okay, so this defines a custom Bahdanau's attention layer subclassing from the tensor flows. Here we have given we have given the tensor flow layers. So it will layer from the you can say from the tensor flow. It will inherit all the behavior. It will inherit all the behavior from the TensorFlow dot Keras library. Okay, so that is the thing. So after that, this init function, basically you already know by now that this basically launches the constructor, or it basically initialize the constructor. But here we have one more function what we have given. This is basically the it's not fitting in this move. So even this also I can put as ATT, because we already know that this ATT is nothing but an attention mechanism. So this units what we have given here. Okay, so this basically refers to the number of neurons used in the building of a neural network. Okay, for forming the internal dense layers. Okay, and here we have this attention scores which can be defined. Okay, so that is what is happening here. Now we are defining the Bahdanau's attention here. Okay, by calling the super function. Okay, so what I'll do is I'll just put like this, and here also I'll just put like this. Okay, then you'll be able to figure it out very easily. So after that, we are going with the self function. Okay, and the first important point to understand what is happening with this layers is these are basically defining each layer. Now let us start with the layer 1. Okay, so this layer 1, this dense layer, the first layer, what it is doing, it's transforming the query vector. Okay, now let me go to the second layer. So the second layer is basically W2, which is the dense layer. Okay, and after that, let me go to the third layer. Okay, which is my V, W1, W2, and V. And my V is basically a dense layer. This will give an actual output of 1. Okay, this will give an actual output of 1. And this is used to compute the score. Okay, at each time. That is the main aim of defining these 3 important layers. Okay, so that is the one thing. Now let us go to the next function, which is query. Okay, so here we have given query and values. Okay, so I'll just put that in a simple note. Okay, so okay, okay. So this is what we have given. So usually the decoder's current state, and that is what the query basically is. And the values are nothing but the encoder's output for all times. Okay. So now let us understand this function, what we are calling first. We are defining a particular function, right? So anyway, you have already understood that here we are using the forward pass. Okay, correct now, right? And the next important thing is we are going with exactly the time axis for that particular query. So query with the time axis, you can see it here. Add here, it's a big, okay. Yeah. So if you see carefully, this particular query with time axis function, query underscore with underscore time underscore axis, the function what you have taken, this is basically taken from the TensorFlow. Okay. So what this actually does is this will change the query size. Okay. So this will actually change from 2 to it will change to 3. Okay. It will change the dimension in a simple way, in a simple language to understand. It basically changes the dimension. Okay. So next thing is calculating the score. Okay. So anyway, when we have learned about Bahdanau, Bahdanau basically usually calculates the score. So that also we have seen what actually it does. So the query W1 basically uses this query with time underscore axis and it transforms into the query. And then the W2 part, what we have, right? It will basically transforms the values, values from the transformation of the values. So this is the second thing which it does. And after this, we have given one particular function here, which is the tan h function. So tan h function will apply both to the particularly for both this W1 as well as W2. And we already know that this tan h function is basically an activation function. Okay, so they are basically a non-linear activation functions. Then we have next thing, which is the self application, which is the self-applying of the V. Okay, here we have defined three layers, no? W1, W2, and V, right? And the same way here, W1 and W2 is basically one is applying or one is actually applying the query with the time axis, and the other is with the transforming the values from the transformational values. This is basically querying to the transform and then values to transform, and combining these two and creating a nonlinear activation function. We are using the tan h. Okay. After that, we are applying the self function, which is the scalar, which applies from one step to the other. Okay. So that is the important thing. What is happening here? Okay, this is actually one step only. I'll just put it in one line. Okay. It will be easy to understand. After that, we are applying the attention mechanism. Okay. Or attention underscore weights. Okay, so how we are applying? We are applying the softmax function here. You can see the softmax function. Okay, the softmax function usually calculates that. Okay, now you have an output like this. Okay, you will have an output with the batch size, maximum length, and one hidden layer. Okay, so that is what will happen. Now, the next point is the context vector. Okay, so what does this context vector actually do? Okay, so this context vector, okay, so next is the context vector. So context vector basically what this actually does, this will calculate the element wise multiplication. Okay, so this is the main important feature of what does this context vector actually do. Okay, so that is one important thing. Okay, we'll do one thing. Put it here. Okay, sorry. Because I have one more comment to add for this one. So yeah, because this is using the reduce function, reduce dot sum. Okay, so we add it here. Okay, yeah, this should help. So coming to this point, the reduce or you can say the context vector, it is from the batch size to the hidden size, and this is basically doing an element-wise multiplication. Okay, and it is taking the attention weights into the values. And the next thing is applying the context vector. This is basically calculating the weighted average of the encoder outputs. Okay. And next thing is the final context vector. This will give the shape, which is the batch size as well as the hidden size. Okay. So this is what basically it happens. Now it will return the values of the context vector first of all. So what exactly is happening in this context vector? So we can add that it is being used as an input to the decoder. Okay. So that is the next important thing. After that, what is happening? It is the attention weights. So often these weights are visualized and these are interpreted when the model is focused on. Okay. So that is what is happening inside the attention for the weights. Okay. So this is, still we have this part to explain. Okay. So, this particular part and this one, we will see it tomorrow. Okay. Because still there is a lot to focus on. Okay. Only till the context vector we have done. Then we have to apply the decoder part with the Bahdanau's, Bahdanau's attention, as well as we have to take an example and apply the forward pass and the backward pass for the Bahdanau's attention. Okay, so along with that, along with this, tomorrow we will see this long attention as well. Okay, we'll try to complete this off tomorrow. Okay, so yeah, if you have any doubts, you can just ping me here. Okay. Okay, fine, ma'am. We can wind up. I think nobody's having any doubts.
Yeah, sure, sir. That's fine. Thank you, sir. We'll meet again by tomorrow at 7.
Yeah.
Yes, students, thank you for joining. We'll meet again by tomorrow at 7 p.m. So we are winding up. Thank you.